In this example, given equation yn minus half yn minus 1 equal to delta n, and the initial condition of y minus 1 is equal to 3. Find yn using Z transform method. So taking Z transform on both sides based on this equation, yn is in Z transform is yz. For this one, you can refer to the table given in the previous slides. So yn minus 1 is equal to this one, or you also can refer this part based on this formula, which is referring to shift property. So this one in Z transform is equal to 1, also included in the previous table. So we settle this one, and applying initial conditions, which is y minus 1 is equal to 3, so we include 3 here. So we settle down this equation, and we take this part without yz to the right side, and we have this one. And for that, we rearrange this equation until we have yz is equal to this one. We take this part to the right side, and based on the inverse Z transform, we know that this part is equal to 1 over 2 with the power of n un. Multiply with the coefficient, the constant 5 over 2. Okay, so this one is equal to Z over Z minus A. In discrete time signal is A with the power of n. So 1 over 2 with the power of n. In the next example, a system is represented by yn plus yn minus 1 minus 6yn minus 2 equal to xn. So given xn equal to 2 with the power of n un, the initial condition y minus 1 is equal to 1 and y minus 2 is equal to 0. Determine the total response yn using Z transform method. So based on the equation given, taking Z transform on both sides, so this one become yz. This one you can refer to the table. Yn minus 1 is equal to this one, z with the power of minus 1 yz plus y minus 1. For yn minus 2, you also can refer to the given table previously. So it's equal to z with the power of minus 2 yz plus z with the power of minus 1 y minus 1 plus y minus 2 equal to xz. So the input xn, 2 with the power of n un, is equal to this one in Z transform, z divided by z minus 2. So subsequently, by applying xz to the right side, and also the given initial condition y minus 1 equal to 1 and y minus 2 equal to 2, so y minus 1 you can apply for this one and this one. Y minus 2 equal to 0 you can apply in this one. So we have this one as our final equation by applying the initial condition and also the exact function. So we have this one. Okay, now we multiply z squared for both sides to remove the z minus 1 and z minus 2 function. So we have this one. So we take the function without yz to the right side, and we maintain this function on the left side. Okay, now we rearrange this equation until we have yz on the left side, and we also divide by z. So we have this equation. So based on this equation, you need to use your partial fraction expansion knowledge to solve this one until you have this equation. Okay, so for this one, for this function, okay, since we have this squared function, you need to solve using this technique. While for this one, you can solve the partial fraction using this technique. Okay, so based on this one, to convert to the to apply the inverse Z transform from this Z equation to the digital time signal, discrete time signal, we can use this formula. Therefore, the inverse Z transform produce the discrete time signal yn equal to this one. For this one, we maintain the constant 2 over 5. Okay, and then it is equal to n multiplied with 2 with the power of n. For this one, maintain the constant 36 over 25. We take this one, 2 with the power of n. Note the difference between this z minus 2 and also z minus 2 squared. For this function, it comes with n. Okay, n a with the power of n. For this one, it is a with the power of n. Okay, and this one, we maintain the constant negative 36 over 25. So since this is positive, so this one become negative 3 with the power of n un.